Hello everyone and welcome to video number 2 in the Transformers course. In this video we are going to cover what is a transformer or what is a transformer construction. Let's start. What is a transformer? In simple terms, you can think of a transformer as a natural extension of magnetic circuit theory. The core guides the magnetic flux along a low reluctance path, while the windings serve as the points where electrical energy is transferred in and out. A time-varying current in one winding produces a changing magnetic flux that links another winding, inducing a voltage on it with no change in frequency. In conclusion, a transformer is a device that converts AC electrical energy at one voltage level to AC electrical energy at another through the action of magnetic field. Or we can say a transformer is a device that consists of two coils magnetically coupled, electrically isolated. Transformer construction. From the transformer definition, the physical basis of the transformer is a mutual induction between two circuits linked by a common magnetic flux. Two circuits magnetically coupled, electrically isolated, as we can see here in this figure. We have a winding on the left side, a winding on the right side, and they are linked together by iron core, laminated iron core. So the core is constructed of thin laminations, electrically isolated to reduce the eddy current loss. So how to select or design these core laminations? One of the key factors that determines lamination design is the operating frequency. As frequency changes, eddy current losses inside the core also change. At standard frequencies around 50 to 60 Hz, lamination thickness is usually somewhere between 0.27 to 0.5 millimeters, with around 0.3 to 0.35 millimeters being commonly used in practice. As we move to higher frequencies, thinner laminations become necessary to keep those eddy current losses under control. For example, in aerospace applications where the frequency is 400 Hz, the laminations will be in the range of 0.1 millimeter. For higher frequencies, 1 kHz and more, ferrite cores can be used. The question now, how to bond these laminations together? They are not simply stacked together loosely. They are carefully assembled to achieve a balance between mechanical strength, magnetic performance, and minimizing losses. To improve magnetic flux continuity and reduce air gaps, the laminations are often arranged in interleaved or step-lap patterns. Different methods can be used to hold these laminations together, including bolts, rivets, clamping, and even laser welding. Laser welding is particularly interesting because only small regions, typically areas with low magnetic flux, are fused together. Please look to the figure. This helps preserve the insulation between laminations and prevents an increase in core losses. Now it's about time to speak about the winding arrangement. So we are going to look for two winding transformer. So it consists of two magnetically coupled windings wrapped around a common laminated iron core, as we explained in the previous slide. So one of the transformer windings is connected to a source of AC electrical power. We call it primary. And the second winding supplies electrical power to the load. We call it secondary. Please look to the figure. We have the primary on the left side here, and we have the secondary in the right side here. So the primary has a certain number of turns N1, while the secondary has a certain number of turns N2. Now the question, how to arrange or assemble the winding together in one core? The first type is a core type transformer. So the iron core forms the main structure of this type. So the windings are placed on two opposite limbs of a rectangular core, as we can see here. The left side, for example, forms the primary and the right side forms the secondary. Where the iron core is formed using these laminations, something like these L-shaped laminations. As we can see here, the flux flows through the core in a loop. So since the winding arrangement is simpler, this type is easy to build and manufacture. They provide medium efficiency and are widely used in distribution transformers and many everyday applications. Now let us look to the second type, which is the shell type transformer. In this type, both primary and secondary windings are wound in the central limb. Unlike the core type, so the core surrounds the winding and the flux splits into two side limbs. So that one is going to provide better magnetic coupling and lower leakage flux, making energy transfer is more efficient. They are also mechanically stronger and more rigid in construction. They are commonly used in high power applications. The third type is the toroidal transformer, which uses a ring-shaped core with winding evenly wrapped around it. Compared to core type and shell type, that one provides high efficiency, lower leakage, less noise, and a more compact design, make it suitable for applications such as audio systems and modern electronic applications and inverters. We noticed in the previous slides that you mentioned for the shell type and toroidal type that the windings are wrapped on top of each other. And even for the core type, we can wind them on top of each other. Why? So we need to answer this question. Another question. Which winding is usually placed closer to the core, primary or secondary? Let us think for this question. If this question is correct, so this question is wrong. Which winding is usually placed closer to the core, the high voltage or low voltage, not the primary or secondary? Because the primary could be high voltage or low voltage and vice versa. So we need to answer these two questions. The first question, why it is recommended to interleave the coils? So the transformer consists of two windings. One of them, called the primary winding, has a number of turns N1 or NP. P stands for primary. And the other winding is a secondary winding, has a number of turns N2 or NS. S stands for secondary winding. So we can wind that one, as we can see here. For example, I'm assuming that the primary is the high voltage and the secondary is the low voltage. So the primary will be in the left side and the secondary will be in the right side. So that one is not accepted. Why? When the primary and secondary coils are wound separately on different limbs, the physical distance increases. So a larger portion of flux do not fully couple both windings. And high leakage is the result, which reduces efficiency and increases voltage regulation. So what is the solution? Interleaving the coils brings the two coils closer, which improves magnetic coupling and ensuring that a greater proportion of flux links both windings, which results in leakage flux reduction and better efficiency, lower losses, and enhances voltage regulation. So we need to prove that one. So let's look for the next slide and how we are going to prove that one. To prove that interleaving the coils will reduce the leakage of flux, I'm going to test the problem using FEMM 4.2 software for the same dimension in both cases, where I selected the number of turns of the high voltage winding is 100 turns and the number of turns for the low voltage winding is 50 turns. The high voltage winding is injected by 1 ampere and the core dimensions are 6 cm height and 6 cm width and the depth is 1 cm. For case number 1, we have the high voltage winding in the left side or the left limb. So the results in this case, total flux will be 20.84 milliweber, flux linkage equals 20.7 milliweber, and the leakage is 147 microweber. And in this case, the inductance, leakage inductance will be 147 microhenry because the current is 1 ampere. Going to case number 2, while the coils are interleaved, so in this case, the total flux will be 20.74 milliweber. The flux linkage will be the same, 20.7 milliweber, while the leakage dropped to 40 microweber. So this construction or this arrangement, we're going to reduce the leakage of flux massively. So winding them close together improves magnetic coupling. This minimizes leakage of flux and increases transformer efficiency and definitely is going to improve the voltage regulation. Second question, which winding is placed innermost or close to the core? The answer is low voltage winding. So low voltage winding could be the primary or secondary. It doesn't make any difference now. So the primary could be the low voltage or the secondary could be the low voltage. But the question is why the low voltage should be close to the core? The answer is improved insulation and safety. The high voltage winding requires better insulation from the core, so by placing the low voltage winding inside, less insulation is needed between the low voltage winding and the core. Another point, the high voltage winding being outside can be insulated more easily from both the low voltage winding and the environment. Point number 2, better heat dissipation. The low voltage winding is usually thicker due to the higher current, and placing it near to the core helps it to dissipate heat effectively. What will I watch in video number 3? In video number 3, we are going to cover the principle of operation and ideal transformer. See you in the next video.